Hi, in this session we shall discuss eigenvalues of the inertia tensor and principal axis transformation. Hi, earlier we defined the moment of inertia tensor. We saw that it has components denoted as I alpha beta is equal to mi delta alpha beta Ri square minus Ri alpha Ri beta. Here delta alpha beta is the Kronecker delta. Ri alpha is the ith component of the position vector Ri vector. Okay. Ri vector, as we said before, is the position vector of the ith particle. Position vector of the ith particle. Right? And Ri alpha is the alpha component of this vector. And sum over I is implied. Repeated indices are summed over. We are following Einstein's summation convention. Since this is a second rank tensor, we can write these elements out as a matrix. Right? We can denote the elements as I11, I12, I13, 21, 22, 23, I31, I32, I33. Okay. But one look at this equation tells us that this is actually a symmetric tensor. That means interchanging alpha and beta does not change the value of the matrix element you are looking at. Because delta alpha beta is clearly symmetric, it's the Kronecker delta. If alpha is equal to beta, it is 1. If alpha is not equal to beta, it's 0. So even if you write this as delta beta alpha, it's going to be the same. Okay. And Ri alpha Ri beta. This is also symmetric because clearly Ri alpha Ri beta is the same as Ri beta Ri alpha. This is just the product of two components of a vector. Right, two different components of a vector. It doesn't matter in which order you take the product, you are going to get the same number. Okay, so we can write I alpha beta is equal to I beta alpha. Now for a symmetric matrix, for a 3 by 3 matrix, there are actually 9 components. Right, or we can say that a second rank tensor has 9 components in 3-dimensional space. Okay, but the condition of symmetry means that all these 9 components are not independent. Okay, for example, if you look at this, I21 here is the same as I12, I31 is the same as I13, I32 is the same as I23. Okay, so if you know the diagonal elements along with these 3 elements, then this matrix is completely determined, or the components of this tensor is completely determined, which means that there are only 6 independent components for a symmetric tensor of this form. We can choose these 6 independent components as these 3 components here along with the diagonal elements. So out of the 9 components of this inertia tensor, only 6 of them will be independent. All right, the 3 along the diagonal plus 3 of the off diagonal elements. Now, just like the components of a vector, I alpha beta here are the components in a given coordinate system. We know that when you rotate the coordinate system, the components of a vector change. In the same way, for a coordinate system of a different orientation, the elements I alpha beta are also different. So just like the components of a vector change when you go from one frame to another frame, when you change the orientation of your coordinate system, the elements of this tensor, the second rank tensor, also change. Now let's look at the defining equation for the moment of inertia tensor. We had L is equal to I omega. This is a matrix equation. L here is the column matrix with elements Lx, Ly, Lz. I is a square matrix. It's a 3 by 3 square matrix with the elements are the components of this inertia tensor, and omega is written as column matrix with elements omega x, omega y, and omega z. Now we already know how the components of a vector change under rotation of the coordinate system. So using that, let's find how the components of this matrix, this inertia tensor, change under rotations. Since L and omega are components of a vector, under a rotation of the coordinate system, they transform according to this equation. L prime is equal to RL, omega prime is equal to R omega. Here R is the rotation matrix. This is the rotation matrix. Okay. So here I have used a different notation for this matrix just to avoid confusion. Right. It's not absolutely necessary that you write it like this. So R here is a matrix, but these elements of the matrix do not form a tensor. Right. I here is also written out as a matrix, but the elements of this particular matrix form the components of a second rank tensor. Right? So I have used a different notation here just to avoid confusion. The matrix denoted with round brackets in this notation are also second rank tensors or tensors in general. All right? This is a first rank tensor. Here we have a matrix in square brackets. These are not the elements of a tensor. This is just a transformation matrix. Now let's look at the defining equation. L is equal to I omega. Let's introduce a rotation matrix to the left and we get R L is equal to R I omega. Okay. Now we can insert a unit or a unit matrix in here in the form R inverse R, because R inverse R is the unit matrix, okay, or the identity matrix. Now RL give the components of the angular momentum vector in the rotated coordinate system. So this is L prime. Okay, this is equal to R I R inverse. Okay, and R omega are the components of the rotated. Sorry, it's the R omega are the components of the angular velocity vector in the rotated coordinate system, which we denoted as omega prime. So we can write L prime is equal to Ri R inverse omega prime. Now we defined the moment of inertia tensor as the linear transformation L is equal to I omega. So this is the linear transformation between the components of the angular velocity vector and the components of the angular momentum vector. What we see here is that the linear transformation between the components of the angular velocity vector and those of the angular momentum vector in the rotated coordinate system is Ri R inverse. This means that Ri R inverse give the elements of the moment of inertia tensor in the rotated coordinate system. Okay, so the component matrix of the moment of inertia tensor that relates the angular velocity to the angular momentum is therefore I prime is equal to Ri R inverse. Now this transformation is called a similarity transformation. This is the similarity transformation performed by a rotation matrix. Now since I alpha beta are the elements of a symmetric matrix, we can always choose the rotation matrix in such a way that the off-diagonal elements are zero. Right? This procedure is called the diagonalization of a symmetric matrix. This means that we can always find a coordinate system in which the matrix representation of the moment of inertia tensor is a diagonal matrix. All right, so you could write this matrix as I1 0 0 0 I2 0 0 0 I3. This matrix has only diagonal elements. This is called a diagonal matrix. So there exists a similarity transformation performed by the rotation matrix such that ID is equal to Ri R inverse, where ID is the diagonal matrix with elements I1, I2, I3 along the diagonal. Non-diagonal elements are all zero. Now for a diagonal matrix, the elements along the diagonal are actually the eigenvalues of that matrix. Okay. So what we have here is the eigenvalues of the moment of inertia tensor. These eigenvalues are referred to as the components of the principal moment of inertia tensor. Now let's say that I is diagonal. The moment of inertia tensor is diagonal in the new set of axes labeled by x prime, y prime, z prime. Then the unit vectors along these axes are known as the principal axis or eigenvectors of the inertia tensor. The principal axis or the eigenvectors of the inertia tensor, they lie along the directions x prime, y prime and z prime. And x prime, y prime and z prime themselves can be obtained by the action of the rotation matrix on the coordinates x, y, z. Okay, we know this thing. We can write x prime, y prime, z prime is equal to the rotation matrix acting on x, y, z. So the principal values of the moment of inertia tensor are the eigenvalues of the inertia tensor, and the principal axis are the eigenvectors of the inertia tensor. The eigenvalue equation, the eigenvalues can be found by solving the eigenvalue equation. We already know this, all right? So if you have a square matrix A, the eigenvalues can be found by solving the characteristic equation A minus lambda I, determinant of A minus lambda I equal to 0, where I here is the unit matrix. We could do the same thing for the components of the moment of inertia tensor, and we get a characteristic equation of this form. Okay, we can expand this determinant. We get a cubic equation in I. We can solve this cubic equation to get three values of the moment of inertia tensor. three eigenvalues of the moment of inertia tensor. We can also find the eigenvectors corresponding to each of these eigenvalues, and these eigenvectors give the direction of the principal axis. So we have seen that there exists a set of coordinates in which the tensor is diagonal with the three principal values I1, I2 and I3. In this coordinate system, the components of L vector would involve only the corresponding component of omega vector. That is, we can write L1 is equal to I1 omega 1 and L2 is equal to I2 omega 2, L3 is equal to I3 omega 3. This is obvious because we could write the transformation equation as L1, L2, L3 is equal to, okay. Now in this coordinate system, if you choose the principal axis as your basis vectors, then we said that the moment of inertia tensor is diagonal. So we can write this as I1 0 0 0 I2 0 0 0 I3. Okay, and then here we have omega 1, omega 2, omega 3. Okay. We see that L1 is equal to I1 omega 1, L2 is equal to I2 omega 2, and L3 is equal to I3 omega 3. So if we choose the principal axis as our basis vectors, then a similar simplification occurs also in the case of kinetic energy. We know that T is equal to omega dot I dot omega divided by 2. We could write this as omega 1, omega 2, omega 3. Okay, this is a row matrix because only then the matrix multiplication will work. And instead of I here, we have the diagonal matrix with elements I1, 0, 0, 0, I2, 0, 0, 0, I3. And this omega can be written as omega 1, omega 2, omega 3. Okay, so this matrix multiplication is what omega dot I dot omega means. All right, we also have a half. So let me write T is equal to half row matrix omega 1, omega 2, omega 3, then the square matrix I, which is diagonal in this basis, and then the column matrix with the components of the angular velocity vector. We could make this multiplication easily. This would become half omega 1, omega 2, omega 3 multiplied by, this becomes the column matrix I1 omega 1, I2 omega 2, I3 omega 3. Right? You could carry out the multiplication again. This becomes half I1 omega 1 square plus half I2 omega 2 square plus half I3 omega 3 square. Okay, so the kinetic energy has a simple form now. It's written as half I1 omega 1 square plus half I2 omega 2 square plus half I3 omega 3 square, where I1, I2, I3 are the eigenvalues of the moment of inertia tensor. Okay. What we have seen is that by using the appropriate coordinate system, we can simplify our calculations. Because if the principal axis are the basis vectors, then the angular momentum, components of angular momentum has this simple form Li is equal to I omega I. Remember, there is no sum over I here, all right? Even though it's a repeated index, there is no sum over I, all right? No sum over I. Alright, this means that L1 is equal to I1 omega 1, etc. And the kinetic energy has a simple form T equal to half I1 omega 1 square plus half I2 omega 2 square plus half I3 omega 3 square. Right, so it's going to be easier to carry out calculations if we choose the principal axis as our basis vectors, or by appropriately choosing our coordinate system, we can simplify the calculations. All right. So with that, I shall conclude. Thank you.